Physical contact with metal defines our daily movement. We turn doorknobs, grab faucets, and push open heavy glass doors without a second thought. Most of us view hardware through the lens of interior design. We select the warm, vintage gold of brass or the sleek, modern silver of stainless steel to match a specific room's vibe. But the finish on a handle dictates more than just the look of a room. This choice involves a specific set of chemical, biological, and economic consequences. One material functions as a natural assassin against microscopic pathogens. The other possesses the capacity to heal its own physical wounds. Understanding which metal dominates our built environment requires an examination of their invisible atomic recipes. Stainless steel is an alloy composed mostly of iron, reinforced with a critical dose of chromium. Curious? In this atomic cross-section, that chromium creates a protective shield. It forms a passive layer, a microscopic film of chromium oxide, that prevents the oxygen in the air from reaching the iron beneath it. This makes the steel stainless. When a deep scratch gouges the surface, the surrounding chromium atoms instantly react with the air to seal the breach and heal the metal in real time. This durable, self-repairing skin comes with a physical trade-off. Stainless steel is a poor conductor, transferring both heat and electricity with high inefficiency compared to other common metals. The material is also a staple of the circular economy. Over 50% of all newly manufactured stainless steel comes directly from massive piles of melted-down scrap. Stainless steel operates as a highly recycled, chemically reactive skin, prioritizing continuous self-preservation over thermal efficiency. Brass relies on a different atomic architecture. It is a precise alloy of copper and zinc, entirely devoid of iron. The absence of iron means brass physically cannot rust. Instead, when exposed to salty coastal air, the salt leaches the zinc away, leaving behind a porous, greenish-blue crust known as verdigris. This high copper content enables the oligodynamic effect, a phenomenon where metal ions exert a toxic effect on living cells. In this visualization, copper ions act like microscopic needles, dismantling the cell walls of invading bacteria and turning the metal into a natural sanitizer. In manufacturing, brass presents an economic paradox. While the raw copper makes it more expensive by the pound than steel, factories favor it because it is free cutting. The alloy's softness allows it to glide through industrial drills at high speeds, reducing the wear on machinery and lowering the long-term cost of tool replacements. However, this composition makes the material hazardous to repair. Welding brass using standard high-heat methods releases a cloud of poisonous zinc fumes. Brass functions as a biologically active tool, sacrificing physical toughness for manufacturing speed and public hygiene. These atomic properties dictate success or failure in the macro world, turning material selection into an environmental matching game. Stainless steel dominates high-impact architecture. Its self-healing chromium shield allows structures to endure decades of rain and pollution without losing structural integrity. But stainless steel has a fatal mechanical flaw: galling. When two unlubricated steel parts rub together, the extreme friction can cause them to cold weld and tear each other apart. That low-friction softness makes brass the ideal choice for moving parts. With its thermal conductivity and germ-killing properties, it remains essential for electrical grids and hospital wards. Placing the right metal in the wrong environment results in fused machinery, toxic fumes, or the unchecked spread of infections. We return to that initial, everyday interaction. Everyday hardware functions as a purpose-built atomic machine, executing invisible tasks around the clock. The next time you grab a door handle or turn a faucet, your fingertips interact with an active, microscopic chemical battleground.